So I'm Xiaoyi from the Chinese University of Hong Kong. I'm very excited to be here and share our work, BlockScope, detecting and investigating propagated vulnerabilities in fork blockchain projects. This is a joint work by my fellow student, Yu Fang, and my PhD advisor, Dao Yuanwu, and Professor Li Xiaojiang from Singapore Management University. We know that Bitcoin and Ethereum are open source, so it's common for those projects to fork their code or partially reuse their code for their own needs. So if Bitcoin introduces a vulnerability, these fork projects may also occur these vulnerabilities. So for example, Bitcoin released a critical vulnerability with a severity score of 9.8 in 2021. Unfortunately, after 2 years, we still identify the same vulnerability in those 5 fork projects. So this leads to a question, is this a common case? If so, we want to detect all these propagated vulnerabilities. And if the vulnerability is fixed, we want to know how long does it take the fork projects to fix the vulnerability. Therefore, we proposed BlockScope, a novel patch-based clone detection tool for propagated vulnerabilities in fork blockchain projects. Specifically, BlockScope extracts the context information from a security patch, and we use this context information to locate possible code clones in the target repository. And by comparing the patch code and the candidate code, we can determine the patch status. BlockScope has 2 unique designs. The first one is that it leverages a patch code context to locate only potential relevant code. And the second unique design is that it adopts a similarity-based code match for being immune to different types of clones. The first one is the context-based candidate clone search. Here we list an example of the code clone in Dogecoin and Bitcoin, where we can see that the up contexts and down contexts of these 2 parts of these 2 codes are almost identical. But for Dogecoin, we can see that the middle part is more similar to the vulnerable version of the code. Thus, we can see that this is the case of vulnerable code clone. Guided by this example, if we want to determine the patch status, we need to first locate the up context and down context by fetching, and then by fetching the middle part, we can determine the patch status. Therefore, we first extract the tokens from each context, and we leverage git grab to find these tokens in the target repository. And then after we find these key statements, we check all the nearby statements to find the boundary of these up-down contexts. And then we measure the similarity of these contexts. If the similarity exceeds a threshold, we can see that this is a clone. And then we fetch the code statements in between and determine its status. The second one is that we designed a new way of calculating the code similarity. In this case, given the source code S with P statements and target code T with Q statements, as we want to cover different types of code clones, as we know that the type 3 clones may introduce the insert or delete codes. Thus, this P may not be equal to Q, as shown in this example. In this case, we first pair up all the code statements in these 2 codes, and then we add their similarity. Also, note that the order issue of these 2 codes may be different, and this order issue need to be influence the similarity of these 2 code fragments. Therefore, we introduce a reverse factor R here to adjust the similarity of these 2 code statements. Specifically, we times this R to the difference of ING, where ING refers to the index of the code statements in these 2 code fragments. In this case, the R to the difference of ING indicates that the greater ING I minus 3, the smaller the similarity between the code statements. And finally, we add up all the weighted similarities and normalize the value into 0 to 1. Note that there are many other tools targeting on a similar problem. Specifically, Redebug is among the most popular one because it's generality and it's public code. It uses the hash of several tokens for the code matching, but it cannot detect the type 2 clones, which means that the code has only repetitions in literal types as such. And we can see that in this example, we can see the type 2 clone change the original main into minimum. And following Redebug, Vadi uses this variable abstraction for more scalable code clone, but it cannot detect type 3 clones, where type 3 clones, as we previously mentioned, introduce a inserted or deleted code statements. In this case, we can see that the type 3 clone adds a int x equals to y statement. Similar to Vadi, MVP and vgraph conduct a more program analysis that they use the program slicing and the code property graph to generate its fingerprints for the codes. And as we can see, all these tools, they use hash-based exact code match for the basic unit. And what they do is they try to generate better hashes for these functions or this code. And moreover is that as they require the program analysis and like function over abstraction, they are language dependent, and compared with some, BlockScope take a complete different path that we do not use the hashed base unit, and we design a better way to calculate the code similarity. We focus on the context to speed up the code search, and we use the similarity measurement to cover more clone types. So BlockScope requires two sets of dataset. One is the target code repository, and another one is a security patch. For the target code repository, we select all the 11 Bitcoin fork projects among the top 100 market cap. And for Ethereum forks, we select the 6 popular projects from Blockchain. And for the security patches, we have 3 simple principles. First one is that the patch should be within 5 years. Otherwise, the fork projects have already fixed the project when the fork projects initialized. And the security patches should cover different vulnerability types so that we can evaluate the generality of BlockScope. And the last one is that the patch should be applicable to most fork blockchain projects. As a result, we select 22 Bitcoin vulnerabilities, including 4 CVEs and 6 CVEs from Ethereum. This is the result. As we can see that BlockScope can detect 40 more true vulnerabilities than Redebug and achieves a precision and recall at both 91%. We can see that even though Redebug has less false positives, it has too many false negatives because it uses a hash-based exact match. And for similarity, for performance, we can see that BlockScope is also much faster than Redebug because the line of code of each project significantly affects the Redebug's performance. Then we want to know why BlockScope has a more effective performance than this Redebug. And as we can see that the type 1 and type 3 clones occupies 95% of all the cases, and BlockScope achieve promising results for all the 3 types. Redebug, on the other hand, can only detect 26% of the type 3 clones and even fails to detect any one of the type 2 clone. And as an ethical research and validation of the detected vulnerabilities, we report all the 110 vulnerabilities to the developers. We received 74 positive response, and we got 2 CVEs, new CVEs from Dogecoin and Litecoin, and a bug bounty from Binance. We can see that 6 projects, including Dogecoin, Litecoin, and Dash are the most active ones, and 3 projects, Bitcoin Cash, Digibyte, and Optimism, did not respond to any of our reports. And with the obtained vulnerabilities, we want to know how do these vulnerabilities propagated to the fork projects. And as a result, we summarize them into 3 types. The first one is the fetch, the fork type, which means the vulnerability is there when the fork projects initially just clone their code from the original project. We have 41 cases of this type. And the second type is the fetch type, which means the vulnerability is fetched from the later commits in the original project. And we have 25 cases of this type. And the last type is that the vulnerability is caused by several commits. And we have 44 of this type. Note that the BlockScope also occurred 18 failed cases. And the first type is that it caused 7 cases of false positives. And we can see that in this case, the fork project indeed did not clone the vulnerable commit, but we used the patch code to test this project, and it caused a false positive. And the second type also is a false positive type. And in this case, the fork project indeed cloned the vulnerability, and it applied the patch, but the source project used 2 patches to fix this vulnerability. We used the latest patch to test this vulnerability. Thus, we got a false positive. And the last one caused 7 false negatives. In this case, the fork project indeed has cloned the vulnerability. And also, this vulnerability is fixed by 2 commits in the original project, but the fork project didn't fetch any of the fixed commits. And we used the latest patch code to test this one, and we got this false negative. Note that the BlockScope can also detect the fixed cases in this case, and we want to know how long does it take for the fork projects to fix the propagated vulnerabilities. In this case, we regard the interval between the patches commit date in the source project and the patches release date in the target project as the patch delay, because finally, the result date is the actual time that the patch is available to the end users. So we first use git blame to find the commit that add the patch. In this case, we can see that this patch is added by 2 commits. This 827.1 and 797F. By extracting the commit date of these two commits, we know that the 827 is earlier. In this case, we can determine that 827 is the actual commit. Since we want the release date, not a commit date, right? And the local Git repository does not contain any release information, so we need to crawl the GitHub repository and find its release date. As a result, we can see these 2 figures where the x-axis is the delay number of delay days, and the y-axis is the CDF. The left one is the plot for Bitcoin, and the right plot is for Ethereum. We can see that only Digibyte can catch up with Bitcoin's schedule, and Dash is particularly slow, as only 30% of the vulnerability can be fixed within 800 days. And for Ethereum, we can see the result is much better. as more than 80% of the vulnerability can be fixed within 200 days. So in summary, we propose BlockScope, and which detects 101 true vulnerabilities in 16 Bitcoin and Ethereum fork projects. We got 2 new CVEs assigned and a bug bounty from Binance. And we conduct a deep investigation on vulnerability propagation and patching process. Thank you for listening. Any questions?
I'm Mizu from KAIST, Korea. So the analysis is based on the coin similarity, right? Maybe I missed the first part, but what's the blockchain specific aspect of your tool? Is there any so blockchain specific, or is it just a generic tool that you can use it for any other projects?
It's generic only. I think it depends that the project is indeed a fork of the original project, which means that the code similarity is higher than any other projects. So it can be used in our systems, but in this work, we only test on the blockchain systems.
Yeah, thanks. A follow-up question. So I noticed that some projects are like forking Bitcoin, but not the entire project, but for example, only the networking layer of Bitcoin. So how did you include those situations as well?
Yes, sure. What we do is that we use the tokens from the security patch, and we use the tokens to search for those tokens in the target repository. So if these tokens have overlaps, we can cover this case. But if they changes all the, for example, they use some obfuscation, and we cannot cover the case.